Welcome to the debate. Imagine this. If a commercial jet completely loses all engine power at 35,000 feet, what happens next? Does it just plummet, or does it transform into something else entirely?
Yeah, it's a terrifying scenario.
Right. Well, today we are looking at the dynamics of rare dual engine failures. My position is that the fundamental guarantor of survival in that moment isn't human intervention, but, intrinsic aerodynamic engineering, specifically high glide ratios. The machine itself ensures survival.
And I will argue that engineering merely buys time. I mean, a mathematically perfect wing design is a wonderful thing, sure. But the true safety factor is the pilot's specialized training and execution.
Okay, well, let's start with the physical reality of the aircraft. Modern jets are remarkably over-engineered. If both engines fail, they absolutely do not fall.
Well, they do glide down, yeah.
Exactly. They boast impressive glide ratios, often sitting right around like 18-1. That means losing 1 mile of altitude buys you 18 miles of forward travel. So if you lose power at 35,000 feet, you have roughly 100 miles of glide range. The aerodynamics alone dictate that the aircraft remains airborne.
I don't dispute the 18-1 ratio, but to any doubting Thomas viewers out there thinking the plane just magically flies itself now, chew on this. 100-mile glide range is functionally useless without a pilot to maneuver it. And by the way, if you want to know how they actually pull off that maneuvering, keep watching till the end of the video.
Oh, it gets really intense.
Because you're suddenly sitting in a 200-ton glider that was fundamentally designed to rely on hydraulic and electrical power from those dead engines. Gliding 100 miles only matters because it buys minutes to run checklists, attempt restarts, and find a runway. The airframe doesn't land itself, It just postpones the ground.
Yeah, but the airframe changes the nature of the emergency entirely. It effectively turns the situation into a giant math problem, where altitude is the only currency the pilots have left to spend.
Right, but think about how they have to spend it.
The engineering provides that exact currency, though.
Sure, but without engine bleed air, normal hydraulics are gone. The only reason that 18-1 glider ratio matters, the only reason the pilot can even steer is because a small windmill called the ram air turbine, or RAT, drops from the belly to power the flight controls.
Exactly. And the RAT deploys automatically. It's another baked-in engineering failsafe. It gives the pilot just enough hydraulic pressure to pitch the nose down and trade that altitude for airspeed.
Just enough to maintain basic control. Yeah.
Right, to keep the wings generating lift. Given all that, isn't the airliner essentially a highly efficient sailplane at that point? I mean, the pilot is just managing the energy budget the engineers already built into the design.
Calling it a sailplane completely ignores the cockpit reality. You don't just let go of the stick and coast. It's less like a sailplane and more like a high-stakes game of orbital mechanics.
Wow, orbital mechanics?
Yeah. The engineers gave the pilots a specific budget of potential energy, yes, but the pilots have to spend every single joule perfectly to reach a runway.
Because there are 0 go-arounds in a glider.
None. You have 0 thrust. You have to calculate descent rates, configure drag, and hit a runway you only get 1 single attempt at. If the pilot misjudges the energy management by a fraction of a percent, that mathematical wing design doesn't save them. History's successful dead-stick landings aren't just aerodynamic inevitabilities, they are operational triumphs.
But they wouldn't even be in the game without the physics of the wing creating that survivable envelope. The successful unpowered landings we've seen in aviation history are only possible because of the predictable mathematics of glide distances.
The math is predictable, sure, but the environment isn't. You have crosswinds, unpredictable weather, and the immense psychological pressure of a silent cockpit. The engineers give you the raw materials, but managing a 200-ton dead weight through a complex descent profile is entirely a human achievement.
Which brings us back to our opening question. When a jet loses power at 35,000 feet, it doesn't plummet. It transforms into a 100-mile glider, and it reaches the ground safely through a profound interception of 18-to-1 physics and elite crew resource management.
We certainly converge on the fact that both are absolutely vital. You can't land a falling brick, no matter how skilled the pilot is. And, well, you can't land a massive glider without a human calculating the precise trajectory to a safe runway.
It leaves us with a compelling question. When the engines go quiet, is it the flawless math of the machine or the pressurized resilience of the human mind that ultimately catches us when we fall? We'll leave you to weigh that balance.
And thanks to everyone for your time today. We'd highly request that you revisit King's Academy for more knowledge and deep dives like this.
Yes, please let us know your opinion in the comments section. And as always, we read all posted comments and reply as soon as possible.